in this video, we are going to continue the final exam review, part 1. We are on question 21. So in this problem, let's figure out exactly what the function is saying, and then we'll take some little notes, and we should be able to get the question pretty good. It says, Chris and Jen decided to go apple picking to a local apple orchard. As the number of apples they pick increased, the cost of the apples also increased. The function f relates the varying cost of Chris and Jen's apples C in terms of the varying number of pounds of apples that Chris and Jen pick, n. So they said that C, the cost, is f of n, which is 0.5 n plus 7. So which of the following describes this notation? So what that's saying is that inverse notation, that the cost is 33. So it's how many pounds of apples did you pick when the cost is 33. So this would actually be the n, the pounds. So which of the following best describes the meaning? So that is the number of pounds of apples when the total cost is 33. Now, how could you find it? Well, 33 equals the y value, or the f of n value, or the c value. So if you just set that equation equal to 33, you're going to find it. So what we're going to do here is we're going to go ahead and solve it for n. So you're going to subtract 7 from both sides. 33, if we take 33 minus 7, you get 26. And then if you divide both sides by 0.5, you get 52. So that would be 52 pounds. Okay, so now it says describe the rule. And do you see how they're solving it for C? So let's take the information up here. Let's take this right here. And let's find C equals 0.5 n plus 7. Let's write that down. C equals 0.5 n plus 7. And let's solve it for n. Okay, so we're just solving for the opposite variable. So C minus 7 equals 0.5 n. So n is C minus 7 divided by 0.5. And that's what they want. They just want you to rearrange and solve for the opposite variable. So I'm going to put C minus 7 in parentheses divided by 0.5. And then we'll look at that. So that's all they're looking for 21. Do you understand that inverse notation? And if you understand that, you're good to go. Okay, let's take a look at 22. Now 22 says, for each of the following expressions, determine the formula that reverses the process. So see how they want our answers in the form x equals. So it's the same thing. We're solving for the opposite variable. So I'm going to do 2 of the harder ones, and none of these are very difficult. So let's do B and E. B and E, okay. The rest you can do on your own, I'm pretty sure. To reverse that 2/3 x and get your x by itself, you want to multiply both sides by the reciprocal of 2/3. So I just wanted to show you that. To divide by 2/3 is to multiply by the reciprocal. So what you get is that x is 3/2 y. So x equals is what we always want to start with. That's what they told us. And that's 3/2 y. Okay? And then we can check that to make sure that's what they're looking for. Perfect. Now let's do this bottom one. Now there's a variety of ways you can do it. If you want to distribute the 5, go ahead. That's perfectly acceptable. what I'm going to do is I'm going to kind of just reverse things. I'm going to add 2 to both sides. I'm going to divide everything through by 5. So then I don't even have to distribute. And then that's x plus 4. And then I just have to subtract 4 from both sides. So y plus 2 over 5 minus 4 is equal to x. Now make sure for iMath that you put that in parentheses. I'd say that's a good thing to do. So we always got to start with x equals. That's what the instruction said. And so that's the quantity of y plus 2 divided by 5. I'm going to kind of skip a space and then go minus 4. And then if you look at a preview, it looks what we thought the answer was. And then let's submit it. So that's a little bit about how we're reversing that reverse process. So they're just kind of talking about what you would do if you're looking for an inverse. Okay, so now we're to our exponentials. You might remember we did those. So let me kind of show you a little, I don't know, I'll show you kind of a formula that can help you maybe a little bit. So if we have this P is our starting value, R is our rate of change. How is that number different than 1? If it's above 1 or below 1, that will tell me if my population is increasing or decreasing. And then N is, in this particular case, it said years since 2011. Okay, so in our first problem, what is the population in the town in 2011? That's that initial number, that P, 7087. What percent does the population change each year as the number of years since 2011 increases? Well, if we look at that 1.45, just take off 1, and that is the decimal equivalent of how it's changing. It went up. It's a positive change. And so if you move the decimal place 2 places to the right, that is a change by 45%. They already have the percentage symbol marked, so I'm going to leave it as 45. Let me go ahead, please, and hit submit just to check our work. Okay. And then it says, use this function notation to represent the anticipated population of the town in 2020. Well, if we do 2011, if we take off 2011 from 2020, that's a 9-year change. So our function was h in this particular problem. So we're just going to find h of 9. Now, they didn't say to calculate it. They just said use function notation. So I think they just want h of 9. Let me just check. Okay. Great. And then it says, what is the anticipated population in 2020? Well, we just found that we have to stick 9 into our function. So we're just going to put 9 into that function. So pull out your calculator, my goodness gracious. Pull out your calculator and stick that in. So 70, I'm sorry guys. 7087 times 1.45 to a power of 9 gives us, now it does say round up to the nearest whole number, so please watch all of their instructions on things like that. I'll be looking at your work, but if you could please try to follow that instruction, that would be very good. If you look at a calculator, it said 804.9, which so then would round up to 200,805 for me. And then the problems that follow are exactly the same, so I'm going to let you handle that. Okay, now let's move on to problem 24. Now, in problem 24, it says that Joni is considering a job offer with 2 companies. Company A offered a starting salary of $63,000 $930 with a 5.9% raise at the end of the year. Company B offered her a starting salary of $58,200 with a raise of $1,900 at the end of the year. What is the ratio of Joni's salary 1 year compared to her salary in the previous year for Company A? Well, let's calculate what her raise amount would be. So if you take 63,000, now you can do this two different ways. You can multiply by 5.9%, 0.059, get the raise and add it on. But I like to do this little trick, added that to 100. That's 1.059. So 100% plus 5.9% is 105.9%, or 1.059 as a decimal. So if you just do that in one fell swoop, you get it. So that would be her total amount. So it would go up to that. Okay. So the ratio of her 1 year salary, that new number I found, $67,701.87, to her original salary, $63,930. Okay. Now, if you look at that, see that how that's that 1.059, we should expect that because that's how we calculated those things. So it's really asking her the 1 year rate of change. So 1.059. If Joni works for Company A, her salary for any year is what percent of her salary from the previous year? Well, it went up 1,900. So we just need to see how is 1,900 related to 58,200. What's that ratio? So I'm going to put that into the calculator because they want that as a percentage. So if I divide that, I get 0.0326. And I'm going to write the main decimals I see there. And then I am going to put, if you move that 2 places to the right, it says there's 0.032646. That would be 3.2646 as a percentage. Let's check to see if they were okay with that. Well, let's see. Joni works for Company A. Oh, I'm so sorry. We're still on Company A. I jumped ahead. Okay. So if Joni works for her salary for any year is always 105.9%. What I was talking about, how 1.059 is the same as 105.9%. Okay, sorry. I jumped into Company B. Okay. Now it says define a function that expresses Joni's varying salary at Company A. Okay. So our function is going to be called f. We are plugging in years. So I'm going to write f of n equals, I'm going to put that starting salary, $63,930, times, and I'm going to put in parentheses 1.059, her new yearly rate of change, to a power of n. Let's make sure they like that. Yeah, there you go. Okay. Now we've moved on to Company B in Part D. It says define a function g that expresses Joni's varying salary at Company B in terms of the varying number of years. Now, we could just make this one a linear function. We don't have to use that percentage since it's so funky. So we know it's going to go up $1,900 every year. And so this time our function is g. And if we look at g of n would be the starting 58,200 plus 1,900 every year. So our years are n. Okay. It says determine Joni's projected salary at each company after 3 years. Now let me just check to make sure my problems are correct. Great. Okay, so I am just going to take what I put in for C and D. I'm just going to plug in 3. I'm going to let iMath do the work because they didn't say I needed to round. They didn't say I needed to do anything. Okay, so for the company A, that would be 639,308. How did they even give that to me for this one? That is totally wrong. 63930. Where'd the 8 come from? How did I make an 8? And where did they give that to me and say, oh, that's good? Okay, I'm sorry, that's right now. Like, I just made a very large salary for Joni. Anyway, 63,930 times 1.059 to a power of 3. And we can even see and write down that preview, but it's there for us, okay? Now let's go to this one. I'm going to plug in 3 into my G function. So 58,200 plus 1,900 times 3. Okay, so then we've got that number. Okay, as use function notation to represent the change in Joni's projected salary. Well, let's check those, make sure they're okay with that. Perfect, okay. Use function notation to represent Joni's projected salary at company A. So we're using the F function from year 4 to year 7. So I'm just going to put and see if they like F of 7. Remember, it's always ending minus start, F of 4. And let's see if that's all they wanted. Yay! Okay, so there is question 24. Let's move on to 25. The following situations, write a formula that gives the value of C in terms of the number of years since the investment was made. Okay, so if it increases by a flat amount like A, or decreases by a flat amount like D, don't overthink it. We would say C equals the original investment plus 67x, because they said x was the number used. Use the correct variables they've asked for. And this one would be C equals 1200 minus 32x. Okay, so those are pretty straightforward there. Okay, now let's look at these middle two here. Now that one is an increase by a percentage, so it needs to look like an exponential function. So it's going to be C equals your starting value times, oh, there's where my 8 came from, times 1 point. Now we're going to increase, so 100 plus or 1 plus 0.13 to a power of n. Oh, x. Here's our x's. Now here we're decreasing, so we need to take 100 minus off the percentage. So if we do that, I think it's 0.9888 if I did that subtraction right. So that would be, we're going to subtract off the percentage. So our C would equal 1,400 times, we're going to use that exponential notation again, 0.9888 to a power of x. So let's go ahead and check that one. There we go. There is question 25. So now let's do one where we find the exponential function from a table. Now, B is a little bit harder than A. So we're going to need to start with A. We're going to do both pieces. Now, the initial value for any exponential function is your 0 number. And they've given that to us in A, not in B, so we do have to do a little bit of work for that one. So that one is just 200. Now the 1 unit growth factor, you'll notice, see how it went down. So let's take 88 divided by 200. And let's see what happens. So 88 divided by 200 is 44%. So it went from 100% down to 44%. So 100 minus 44, well, at final minus beginning. So that's 44%. So it went from 100% down to 44%. So it went down by 56%. So the unit growth factor would be negative 0.56 or negative 56%. Now, I don't want to do anything further until I've checked that. So here, what do they want? The 1 unit growth factor. Oh, I'm sorry. It changed by 56%. The growth factor was 0.44, I think. Would be just that value when we divided. Let me just check to make sure. Okay, so yes, so this was the change, and the other was the actual division. So when you divide that from 1 year to the next, you get 0.44. Okay, so our function is always going to be, now they call this function, if you look in the chart, f of x equals, so our starting value 200 times 0.44 to a power of x. Now let's check it, okay? Okay, now our 1 unit growth factor I would like to do in B as my first step because I don't have my initial value. So if I take my, this time it went up, okay? So if I take my 1 unit, they have to be 1 unit away from each other, and I divide it by the year before, so 32.8536 divided by 28.08, I get 1.17. So that is my 1 unit growth factor. And then, oh, I'm sorry. And that is just my growth factor. So how much did it change? You have to take off 100%. So 117 minus 100 is a positive change of 17%. That's the one we want a percentage, okay? So in order to fill in our function, we do need our initial value. So we have to take that 28.08 and go backwards. Instead of multiplying by 1.17, we need to divide by 1.17. And that will give us our, where did you start? So 28.08 divided by 1.17. We should see it go down, and it came out to be a nice perfect number of 24. So that's our initial value. So now we know our function. So our function, this time the chart says to label it as g. So g of x equals our starting value 24 times 1.17 to a power of x. So that is some exponential functions from a table. Question 26. Let's move on to question 27. Okay, the value of a car depreciates each year. So that percentage of depreciation is going to make our initial value go from 100 down by 9%. So the initial value of the car is that 23,500. The 1 year growth factor is 100% minus 9% or 91%. And so our percent change each year is negative 9%. Our 1 year growth factor is 0.91. If they just say a factor, use the decimal. If they have the percentage symbol there, use the percentage. I think that's what they want there. Let's check. Yeah, okay. So what's our function? They're calling a function f. It's in terms of x. So f of x equals our starting value, 23,500, times 0.91, whatever that 1 year growth factor is, to a power of x. Let's check it just to make sure we're good. Okay. Now that we have a function, C is pretty easy. We just got to stick in 8. Now it says to do some rounding, so let's let iMath do the math for us, and then I'll write the number rounded to the nearest penny on the side. So 23,500 times 0.91 to a power of 8. So that's what it would be after 8 years. Now I'm going to write down that number, so $11,050.93. There's a 4 after the 3, so we're going to keep it a 93. So I'm going to delete that. I'm going to follow the instructions. $11,050.93. So there is question 27. Question 28. Okay, so there's coffee. We did the coffee ones before. 131 milligrams is your starting value. The caffeine is eliminated at a rate of 14.6% per hour. So the rate of change is that percent. It's going down by 14% each hour. Okay, so the growth factor, we always take 100. Minus off that if it's going down, add it if it's going up. So that's 85.4% as a percentage, or 0.854 as a growth factor. So I'm just going to hit submit, make sure we're on the right track for those. Okay. So how much caffeine would remain in a person's body 1 hour after he drank coffee? So I'm just going to make a function. I'll call it caffeine, and then I'll call it hours. It's your starting times our 1 hour growth factor to a power of h. Okay, so 1 hour, you just do 131 times 0.854 to the first, or 131 times 0.854. And so it doesn't say to round, so you could probably just put in 131 times 0.854 if I subtracted right, which I think I did. Or you could probably, when they don't say round, I kind of just let them do the math. The growth, a 2 hour growth factor, we would multiply by 0.8454 twice, or to the second power. And then you can see here, see that, what is that percent change? So we have to think 100 minus 72.9316 would be how much it went down in the 2 hour span. And if you do 100 minus that, you get 27. I guess I could have just typed that in probably. 27.0684. Okay. And it is a going down, so please let's make that a negative. Okay, how much caffeine remains in a person's body 2 hours after? Well, we know that we could multiply by 0.854 twice. I don't see that as an option. That middle one where you're subtracting 0.854, it's not right. If we took, let's see if we do, what is 0.854 times 131? 0.854 times 131 is minus 100. Wait a second. 0.854. Okay, wait, so the percent change in every hour is 14.6. So 131 5, 4. I'm just doing some calculator stuff here, people. Give me a second. Or I think it could be. So 131 times 0.146 is 19.12. I don't think it's any of those because here's the formula. I'm sorry. I was thinking to myself, those aren't right. It's 131 times 0.854 squared. So what I was doing, 854. I was going, are any of those equivalent to that? And they just didn't seem to be working. So I think, yeah, the only one that was close, that second one, that's what we got for the first hour, but not the second hour. We need to multiply by that 0.854 again. So none of those were right. That's why I was kind of like, what? Okay, now let's go on to 29. Okay, so the 1 unit growth factor for this is 0.75. The 2 unit growth factor is 0.75 squared. The 8 unit growth factor is 0.75 to the power of 8. And so the 1/3 growth power, I think you got the pattern here, is to the 1/3. I'm going to put 1/3 like that. See how I put it in parentheses? And so, if I put a 0.75, and then this one is 0.75 to the 1/4. So there you go. Okay. So I don't think we need too much here, except I do want to talk about the percentage change. Okay, so let's go to C and D, and I think that will help you for here. Okay, so the 4 unit growth factor is 1.21 to the 4th. Okay, so look what it shows you over that 2.143. The percent change is how much did it change from 100? So if you just take 100 or 1 off of it, you get 1.143. So 2.1435881 minus 1 is 1.1435881. Move the decimal over, you got a percent. So I think they just want 114.358881. Let's try it. Yeah, so I did want to show you that one. Okay, let's go to 31. Okay, so we have an annual percentage rate formula. So this is one you would definitely want to make sure that you know. That is the formula for annual rate. You might recall there's a formula that has a little n here. It's the same formula. Annual means that n is 1. And so when n is 1, that piece and that piece becomes irrelevant. And so you get that nice formula, okay? So if you have a 5% APR compounded monthly, none of those say annually. Oh, I'm sorry. So that's an annual one. Okay. So that's annual. But if it's compounded different times, we do need the n. I'm sorry. So let's put the n on. Okay. So those formulas definitely you need to know. Okay, so the monthly growth factor, just take your, I'm going to try it 2 different ways. So remember our growth factor, we have to add on the it to 1. So if it's 5% APR, that's annual. So they just want this. So I'm going to put in there 1 plus 0.05 divided by 12. And I'm going to see if that's what they want. I love all the red X's. Okay. So this is the quarterly growth factor. That would be 1 plus 0.067 divided by 4. Quarterly is 4. And this one, a daily growth factor. There are 365 days in a year, so that's 1.0032 divided by 365. So I think what they're doing there is, for that part of the question, they're just setting up this portion of your formula for you. Okay, so let me just check all those. Okay, now what is the annual growth factor? Well, that is compounded monthly, so that's the monthly growth factor. How many months are in a year? 12. So just take what you found in part, what you did in the first part of this question. Type it out again in parentheses, if Mrs. Hawk could type. And then put it to a power of 12. So that same thing you divide by, 12. See the formula? Now what you're doing this part of the formula. So not the P and the T, we're just doing this part of the formula. Okay, so this one would be, in parentheses, exactly what you typed before, 1 plus 0.067 divided by 4 to a power of 4. And then this one would be 1 plus 0.032 divided by 365, parentheses, to a power of 365. Let's check them, just make sure they like what they're seeing here. Great, okay. So the APY, we're going to use the previews. See that annual growth factor? Okay, see the preview there? See how that is a little more than 5%? Okay, so we're actually going to help ourselves if we, I think this will work. If we copy all that into here, how do you change a decimal into a percentage? You got to move the decimal place 2 places to the right, or multiply by 100. See, well, look at your preview. See how it's 105%? Oh, we got to take off 1. No, we got to subtract 100. That might be too complicated. Oh, it works, but okay, let me show you a better way. Okay, let's just look at our preview. See, that's 106, or 1.0687. Move it 2 places over. You're seeing that preview. Let's just do 6.87022514028166. I mean, we're just going to show them all. See if they like that. So you can do my complicated way from the start, or just, okay, let's look at this preview. It should be a little bit more than 3.2%. It is. So it is 3.2516057037474607. I don't know. Okay. There you go. So that is one about this formula we see to the right. So now we've got this formula. They've set it up. So you really need to know what each piece stands for. Okay, the 0.035 divided by 12, since this is compounded monthly, that is the monthly growth factor, so that's a B. Now remember, when we added it up, we added the 1 on, that was the monthly, okay, wait, let's see here. The growth factor, we always add 1, so the monthly growth factor is that. No, this is the monthly growth factor. So what's the 0.035? Okay, I need to go back and look at question, the language they used on question. I don't even know. No. Okay. So the monthly growth factor was the whole thing. Okay, so let's go back. Okay. So the monthly growth factor is the 1 plus 0.035 to the 12. So that is indeed B. And then when we took it to the 12th power, that was our annual growth factor. So this one is A. And then the 6-year growth factor, we need the little 6 on there. So the 6-year growth factor, this one is D. 12 times 6, that's the number of times we get interest in 6 years. So this is C. And then the 0.035 divided by 12 is the monthly percentage change. Okay, so that's just the monthly percent change. That little R over N is the monthly percent change, okay, as a decimal. So that is that one. Let's just check, make sure I got those all right. Okay, so let's just look at this formula one more time so I can kind of take you through it. This piece right here, R over N, is the monthly percent change written as a decimal, okay? The 1 plus R over N, just that plain thing. So B is the monthly growth factor. P is your starting amount. If you take this whole thing just to the nth power, that's what we see in A. That's your annual growth rate. And then if you do it to the time that they say, that is the growth factor for that time, that 6-year growth factor. And so that should kind of take you everywhere. And that 12 times 6 is that NT. That NT is the number of times that your interest compounds in however many years. Okay, so there we go. Okay, determine the value of each account after 13 years. Now, this is when it's compounded a particular number of times. If they use the word continuously, you want to use, remember I called it the PERT formula, okay? So we're going to just put in the PERT formula information each time. So we're doing 4,500 times e to a power of, now put this power in parentheses, you're going to write the rate as a decimal, so 0.043 after 13 years, so times 13. That's it. 650 times e to a power of, in parentheses, 0.069 to times 13. And then the last one, 2100 times e to a power of 0.047. Let's put that in parentheses so we can multiply it by 13. So the compounded continuously formula is probably easier than the others. You just plop that information in, but we only use it when they use the word compounded continuously. Okay, so that's actually a pretty nice formula. Determine the value of the unknown in the following equations. So they just want you to solve it for y. Now, I don't know if this is going to work, but I'm going to try something here. This might be an easy problem for you. I don't know. I'm going to enter in exactly what, because they've solved it for the variable in A and B. Now, that's not going to be the case for the other ones. We do have some work to do for C and D, but A and B, they've solved for your variable. So if we just put in what we got, and we look at the preview, oh, I need one more parenthesis, I'm sorry. If we look at the preview, it says 35, So if I put in 35, yeah, okay. So A and B are gimme. Just type in. You see how I did log base 5, like this one, log, hit the underscore and then 8. That'll bring that down below. And this answer is 0, but yeah, it gives it to you, okay? So the answer to that one's 0. Okay. But C and D, we have to do some work. So I'm going to write down C, and then I'll walk you through that one. So what formulas should you know for this? So you need to know that the log base b of your number equals a power can always be rewritten as your number is your base to your power. So you have to have this written down. You have to know that, okay? Okay. So if we take our log information and we flip it and we make it into our formula, we can solve for k pretty easily. I know that my number, 4 over k, is my power, a base 16 to a power of 1. Well, 16 to a power of 1 is 16. What power could I put on a 4 to get 16? Since 16 is 2 squared, 4 squared, I was thinking of 2, then our power has to be 2, so k has to equal 2. Okay, now that one's pretty good. D is a little harder. Let me write that down. See, we're looking for what base would have done this. And this one's probably our hardest one, but it's actually not too bad. They've kind of made something look a little harder than it needed to. Let's rewrite it. My number is b to a power of 1.5. Well, if you think of 6 as 6 to the first, square root of 6 is 6 to the 1/2. This is, the rule is, if the bases are alike and you're multiplying, add the exponents. So that's 1.5. What power did I use on both? 1.5. So they're irrelevant. 6 equals b. So our answer to this one is 6. So it's a trick one, but it's a pretty cool one there for those ones. So those, I would suggest, make sure you understand how to flip back and forth between our logarithmic form and our exponential form. Here, they are using some things about logarithms and e's. The logarithm, so here's some other rules you want to write down. The logarithm of e to any power is just going to equal the power. So in A, that would simplify down to a 5. It's just going to simplify down to the power. Now, we can use the same trick for B, but just remember that would be e to the negative k. So our answer would be negative k. So we get that negative 6 equals negative k. So k equals 6. And then this one, we would get that m equals 8. So those ones are pretty nice. The only one that's different is C. So another rule, so this is the rule you need. If the e and the natural log are touching like this, it always simplifies down to that number. So this one, they cancel out, leave you with the p. This one, they cancel out, and they leave you with the number. So the number inside here is your 2x. Oh, I don't know what just happened, but I was able to write on that. Oh, that's magic. Okay, I'm so sorry. I just learned something that was kind of magical. Anyway, so for that one, my e to the ln of 2x equals 8. That's just 2x has to equal 8, so x is equal to 4. Oh, so I think I can go like that. Anyway, so my Apple Pencil did some. What was that one answer to? Oh, I'm sorry, 6. So anyway, that is how you do those ones. So make sure you know the two formulas I say I have circled on the right. They just are showing you that e's and natural logs cancel out really nicely. They're inverses. They're opposites. Let's talk about some rules of condensing. So they want you to write this into a single logarithm. So let me write these down, and then I'll kind of expand this so we can see it a little better. Well, I'm going to scooch it over now because I can't. You guys can tell I don't write very tiny. Maybe writing on a board for so many years. Okay. Okay. So in part A, to condense this, the first thing we need to undo is any front number needs to go forward and become a power again. So remember that rule where our power drops down. So let's put the powers back on. So just take your numerical component, whatever's inside your parentheses, put it on as a power. Okay. Now, any pieces that are positive, so this one's positive, is going to put that thing inside of my logarithm in the top, the numerator. We're going to multiply. And here, we are going to divide both those in our denominator. Okay, so we're going to do the log of, put x to the fifth on the top, y to the 1/5 times z squared in the bottom. And that's what your answer should look like. We didn't have a base, so we don't have to do a log underscore anything. Okay, now I need a fraction, so just make sure that you put your top or bottom, if it has more than one piece, put it in parentheses. So I'm going to do a y to the 1/5. You'll see I put that 1/5 in parentheses times z squared. And see what you have down on paper. Does it look like the preview? Does it look like what we have? And it's a perfect match, okay? So let's just give that, okay? Now, B is a little different, not much, but it's a little different because of the fact that we have this -2 quantity in front of this entire thing. So here's my suggestion. Use the distributive property first. Distribute the -2 into both of these things before you make any decisions about where things go or what your powers are. So you see, I just use my distributive property, -2 multiplied by everything. Okay. And then it becomes exactly like A, nothing different. We're going to bring our powers inside. Oh my goodness gracious. So this is the log of y squared minus the log of z to the 6th. So our fraction will only have an x in the top. It's going to have a y squared and a z to the 6th in the bottom. So we're going to have the log, parenthesis, x divided by, parenthesis, y squared times z to the 6th, and my bottom parenthesis and my log parenthesis. It looks exactly like what I have written down on the paper. And there you go. Let's look at 37. Now in 37, we are coming back and doing the opposite. We're expanding it, okay? So we're going to do the log of all the pieces on the top are going to come separate. They have to be multiplied together. They're going to have their own logarithm with a plus between them. And any pieces that are in the bottom are going to have their own logarithm with a minus. So the x to the 13th and the y to the 31st are on top. They're plus. The z to the 36th is on the bottom. It's a minus. And then drop the powers down in front. And so our final answer is 13 log of x plus 31 log of y minus 36 log of z. And there you go. The preview looks like what I want. I'm going to hit submit. Okay, we're almost done with part 1. So it says, find the exact solution of this exponential equation. So you always want to proceed in the following manner. You want to isolate this. So if this front number appears, which could have been your starting value, divide that off. Always divide that off first before you proceed. So let's divide by 20. And we get 100 equals 3 to the 2x. Now, if 100 was a power of 3, so like if it was 27, 81, something like that, you could break down the 100. But when they don't match, we're always going to use the same trick. It's a very nice trick. It works every time. Do the same thing. Stick a natural log in front of both of them. Take the power now and drop it down in front. So we get the natural log of 100. That's just a number. Equals 2x times the natural log of 3, which is just a number. Sorry, I changed colors there. Which I do occasionally, but somehow I tapped it. Okay. So think about if we had x times some numbers and we wanted to solve that equation. You divide, we got it. And that's our exact answer. We don't have to do anything else. So just divide by 2 and the natural log of 3 on both sides, and you have just solved for x. That is our exact answer. We are going to type into iMath the natural log of 100 over 2 times the natural log of x. Not x, what was that? I'm sorry, 3. I'm like, wait, I just moved my x in a weird way. We divided off the natural log of 3, Mrs. Hall. Okay, so I'm going to get the natural log of 100 divided by, in parentheses, my whole entire bottom, 2 times the natural log of 3. I have all my parentheses. They didn't say there's any errors. It looks beautiful and lovely green. And there you go. That's a good 39. Excuse me very much. I'm sorry. Okay. The amount of caffeine, single caffeine, decreases by 24% every hour. A cup of caffeine, define a function that gives the amount of caffeine remaining in the bloodstream T hours. Okay. So remember, this is just going to be a rate of change. It's an exponential function. It's going to be f of t equals our starting amount. Now, we have to take 100% minus 24%, or 1 minus 0.24, which is 0.76. And then it's to a power of t. Now, I'm just going to, kind of peek, and it looks good. How many hours will it take for the amount of the caffeine to reach half of the amount? Okay. Now, we're going to do exactly the same technique we did in the last question for this one. But what's half the amount? Half the amount is 50. So we know 50 is 100 times 0.76 t. Now, what did I tell you in the last equation? This front number divided off. You divide it off, 50 divided by 100. It should be half the amount. So when is that 0.76 t going to equal half? It's exactly the same procedure we did last time. Stick a natural log on both sides so that we can drop the power down in front. So the natural log of half equals t times the natural log of 0.76. So t is going to be the natural log of a half over the natural log of 0.76. That's it. They didn't say that we needed to round to the nearest hour or anything. So let's just put that in. Looks good. They accepted it. It's a number. Yay. Okay. Those are the same. So yeah. So then the rest you can finish. It's exactly kind of the same procedure. Last one. Okay. So we have a formula. It is used to determine the number of milligrams of a drug in a patient's bloodstream. T is going to be hours, and A is the amount of milligrams. How many milligrams were initially given? Well, if we look at the formula, this is always where our initial amount goes, so that would be 5 milligrams. When the number of milligrams of the drug reaches 4.9, how many hours have been since the injection? So I know 4.9 was my final amount, and so this becomes exactly the same trick as before. But something really cool happens when we use a natural log here. So again, first step, you always divide off your initial amount. So I'm just going to write 4.9 divided by 5. I don't care what it is right now. We can do that. iMath can do that. I don't know. But watch what happens. It's something really cool when we use a natural log. Now remember earlier we talked about natural logs and e's are inverses of one another. So if they're inverses of one another, they're going to cancel out really nice. So watch. Natural log, natural log. Ooh, what happens? That's gone. So we just get the natural log of this fraction, if I can write that, equals the power, 0.97t. Because if the power dropped down in front, the natural log of e is 1, and they cancel out, okay? So now we just divide both sides by this, and that's our time. That's how many hours. I'm going to let iMath do it. I don't know. They can do the work. So the natural log of our fraction, 4.9 divided by 5, divided by, I'm going to put that negative in parentheses, just to make it look better, 0.97. And then there's the hours. So does the number of hours between injections depend on the initial amount of the drug given to the patient? Well, it would probably be the rate of change and not necessarily the starting amount. I don't know. We're going to see. Oh, it is, yes. Then. Does the number of hours between injections depend on the initial? Well, okay, so if they gave you initial amount and they can't give you more until so much of it has disappeared, I guess. Okay. So, guess what? Part 1 is done, but you still got part 2 to do. So don't give up now. We're almost there. iMath is almost done. Good luck. There you go.